Jackhammer. A pneumatic drill or jackhammer is a portable percussive drill powered by compressed air. It is used to drill rock and break up pavement, among other applications. Samuel Ingersoll invented the pneumatic drill in 1871. When we saw someone digging a hole in the road with a tool like this, we would probably think the equipment was electric or powered by a diesel engine, right? In fact, the only energy involved in making a jackhammer pound up and down is supplied from an air hose. The hose, which has to be made of especially thick plastic, carries high-pressure air from a separate air compressor unit powered by a diesel engine. The air compressor is a bit like a giant bicycle pump that never stops blowing air. The long wooden handle and metal blade act like levers to magnify the force you generate with your back muscles and arms. It's simple technology, but it's very effective. When the worker presses down on the handle, air pumps from the compressor into the jackhammer through a valve on one side. Inside the hammer, there's a circuit of air tubes, a heavy pile driver, and a drill bit at the bottom. First, the high-pressure air flows one way round the circuit, forcing the pile driver down so it pounds into the drill bit, smashing it into the ground. A valve inside the tube network then flips over, causing the air to circulate in the opposite direction. Now the pile driver moves back upward, so the drill bit relaxes from the ground. A short time later, the valve flips over again and the whole process repeats. The upshot is that the pile driver smashes down on the drill bit over 25 times each second, so the drill pounds up and down in the ground around 1,500 times a minute. A skilled drill operator can loosen chunks of road in just 10 to 20 seconds, making light work of what our ancestors with their antler picks would have found truly back-breaking work. Light stick or glow stick. A glow stick is a single-use translucent plastic tube containing isolated substances which, when combined, are capable of producing light through a chemical reaction-induced chemoluminescence, which does not require an electrical power source. Light sticks are just one application of an important natural phenomenon, luminescence. Generally speaking, luminescence is any emission of light that is not caused by heating. Light is a form of energy which can be emitted through a variety of processes. These processes include incandescence, fluorescence, and phosphorescence. Laser generation. All these processes work on the same basic principle. An outside source of energy excites atoms, causing them to release particles of light called photons. A light stick does the same basic thing, but it uses a chemical reaction to excite the atoms in a material. This chemical reaction is set off by mixing multiple chemical compounds. Compounds are substances made up of atoms of different elements bonded together in rigid structure. When you combine two or more compounds, the various atoms may rearrange themselves to form new compounds. Depending on the nature of the compounds, this reaction will cause either a release of energy or absorption of energy. The reaction between the different compounds in a light stick causes a substantial release of energy. A typical commercial light stick holds a hydrogen peroxide solution and a solution containing a phenyl oxalate ester and a fluorescent dye. Before activating the light stick, the two solutions are kept in separate chambers. The phenyl oxalate ester and dye solution fills most of the plastic stick itself. The hydrogen peroxide solution, called the activator, is contained in a small fragile glass vial in the middle of the stick. When you bend the plastic stick, the glass vial snaps open and the two solutions flow together. The chemicals immediately react to one another and the atoms begin emitting light. The particular dye used in the chemical solution gives the light a distinctive color. Depending on which compounds are used, the chemical reaction may go on for a few minutes or for many hours. Loudspeaker. A loudspeaker, speaker or speaker system is an electroacoustical device that converts an electrical signal to sound. An object produces sound when it vibrates in air. When something vibrates, it moves the air particles around it. Those air particles in turn move the air particles around them, carrying the pulse of the vibration through the air as a traveling disturbance. Sound is invisible most of the time, but sometimes you can actually see it.
If you thump a kettle drum with a stick, you can see the tight drum skin moving up and down very quickly for some time afterward, pumping sound waves into the air. Loudspeakers work in a similar way. A loudspeaker produces sound waves by rapidly vibrating a flexible cone or diaphragm. The cone, usually made of paper, plastic, or metal, is attached on the wide end to the suspension. The suspension or surround is a rim of flexible material that allows the cone to move and is attached to the driver's metal frame called the basket. The narrow end of the cone is connected to the voice coil. The coil is attached to the basket by the spider, a ring of flexible material. The spider holds the coil in position but allows it to move freely back and forth. When you hook up the loudspeaker to a stereo, electrical signal feed through the wires into the coil. This turns the coil into temporary magnet or electromagnet. Depending which direction the electricity flows in, the electromagnet either attracts or repels the permanent magnet. This moves the coil back and forward, pulling and pushing the loudspeaker cone. Like a drum skin vibrating back and forth, the moving cone pumps sounds out into the air.
Piano. The piano is a musical instrument played by means of a keyboard that produces sound by striking steel strings with felt-covered hammers. The invention of the modern piano is credited to Bartolomeo Cristofori of Padua, Italy. A piano sounds quite unlike any other instrument, and if you heard it on the radio, you'd probably never guess how it was making a noise. The confusing thing about a piano is that it's two different kinds of instrument in one. It's a string instrument because the sounds are made with strings, but it's also a percussion instrument because the strings make sounds when something hits them. So what happens when you press the key of a piano? When you press down on a key, the opposite end of the lever jumps up in the air, forcing a small felt-covered hammer to press against the piano strings, making a musical note. At the same time, at the extreme end of the lever behind the hammer, another mechanical part called a damper is also forced up into the air. When you release the key, the hammer and the damper fall back down again. The damper sits on top of the string, stops its vibrating, and brings the note rapidly to an end. To make the sounds louder, there is a large piece of wood mounted underneath them called the soundboard. When the strings vibrate, the soundboard also vibrates. The soundboard effectively amplifies the strings so they are loud enough to hear. The lid helps the audience too. Sound from the strings and the soundboard travels straight up, hits the lid, and reflects out towards the audience. While the 88 keys on a piano control the music notes that the pianist can make, the 3 pedals determine how loud or soft these notes are and how long they last. The pedals on the left is called the soft pedal. Most of the keys on the keyboard hit 2 or 3 strings simultaneously when you press them, so you get a richer and a louder note. However, if you press the soft pedal down, the hammers that play the notes shift slightly to one side, so they contact fewer strings, making a quieter note. The middle pedal is called the sostenuto pedal. When you press it down, it temporarily deactivates the dampers for the notes that you're playing at the time and makes them last quite a bit longer. The pedal on the right is called the sustaining pedal. Pressing it down raises all the dampers up in the air so all the notes last longer. Radar. Radar is a method of detecting distant objects and determining their position, velocity, or other characteristics by analysis of very high-frequency radio waves reflected from their surfaces. The word radar stands for radio detection and ranging. Several inventors, scientists, and engineers contributed to the development of radar. The first to use radio waves to detect the presence of distant metallic objects was Christian Holzmeier. Whether it's mounted on a plane, a ship, or anything else, radar set needs the same basic set of components: something to generate radio waves, something to send them out into space, something to receive them, and some means of displaying information so the radar operator can quickly understand it. The radar waves are generated by a piece of equipment called a magnetron. Radio waves are similar to light. They are made up of fluctuating patterns of electrical and magnetic energy, just like the light waves, and they travel at the same speed. But the waves have much longer wavelengths and higher frequencies. Once the radio waves have been generated, an antenna working as a transmitter hurls them into space. The antenna is usually curved so it focuses the waves into a precise, narrow beam, but radar antennas also typically rotate so that they can detect movements over a large area. The radio waves travel outward from the antenna at the speed of light and keep going until they hit something. Then some of them bounce back towards the antenna in a beam of reflected radio waves, also traveling at the speed of light. Any reflected radio waves picked up by the antenna are directed into a piece of computerized electronic equipment that processes and displays them in a meaningful form on a television-like screen, watched all the time by a human operator. The receiving equipment filters out useless reflection from the ground, buildings, and so on, displaying only significant reflections on the screen itself. Using radar, an operator can see any nearby ships or planes, where they are, how quickly they are traveling, and where they are heading. There's one more important piece of equipment in the radar apparatus. It's called a duplexer, and it makes the antenna swap back and forth between being a transmitter and a receiver. Radar is something that is in use all around us, although it is normally invisible. Air traffic control uses radar to track planes both on the ground and in the air, and also to guide planes in for smooth landings. Police use radar to detect the speed of passing motorists. NASA uses radar to map the Earth and other planets, to track satellites and space debris, and to help with things like docking and maneuvering. The military uses it to detect the enemy and to guide weapons. Meteorologists use radar to track storms, hurricanes, and tornadoes. Stethoscope. A stethoscope is a medical instrument used to listen to sounds produced in the body. It is most often used to listen to ear sounds and breathing. It is also used to listen to intestines and blood flow in arteries and veins. The stethoscope was invented in France in 1816 by physician René Laennec. There are two types of commonly used stethoscopes, electronic and acoustic. Acoustic stethoscopes consist of a chest piece, two hollow air-filled tubes, and the earpieces. There are normally two sides to the chest piece, the diaphragm, a plastic disc, and the bell, a hollow cup. When the diaphragm is placed against the patient, the sounds of the body vibrate the plastic disc and acoustic pressure waves are formed. These pressure waves travel up the hollow tubes to the listener's ears. The diaphragm side of the chest piece is useful for transmitting high-frequency sounds. If the bell is placed against the patient, the vibrations of the skin directly produce acoustic pressure waves that travel up the hollow tubes to the listener's ears. The bell side of the chest piece is used to transmit low-frequency sounds. Telephone. The telephone is a telecommunication device that is used to transmit and receive sound, usually two people conversing, but occasionally three or more. It is one of the most common household appliances in the world today. Most telephones operate through transmission of electric signals over a complex telephone network, which allows almost any phone user to communicate with almost anyone. In the 1870s, two inventors, Elisha Gray and Alexander Graham Bell, both independently designed devices that could transmit speech electrically. Both men rushed their respective designs to the patent office within hours of each other. Alexander Graham Bell patented his telephone first. The very simplest working telephone would look like this inside. As you can see, it only contains three parts and they are all simple. Speaker, microphone. The microphone contains carbon granules and a thin metal diaphragm. When you speak, the sound waves hit the diaphragm and causes it to move, compressing the carbon granules behind it. A louder sound will compress the granules more than a soft sound. When the carbon is compressed, an electrical current can flow through it more easily. A battery sends an electric current through your phone. When you speak, the compression of the carbon varies the intensity of the current.
This process is reversed at the other end of the line by the receiver. The electrical current flows through an electromagnet in the receiver, producing a magnetic field. This magnetic field attracts the thin metal diaphragm in the receiver, causing it to move in and out. As it does so, it pushes and pulls the air, creating sound waves. These waves reach your ear with the same intensity as they were spoken, allowing you to hear what the other person said. Now, how does people get connected through a telephone? The following are the steps involved. The signal leaves your house to a telephone box outside. The local exchange is connected to all the phones in a small geographical area. From the local exchange, calls are routed to the main exchange. The main exchange may route the call to another. Television. The device we call the television is really a television receiver, that is the end point of a broadcast system that starts with the television camera or transmitter and requires a complicated network of broadcast transmitters using ground-based towers, cables and satellites to deliver the original picture to our living rooms. In 1928, Philo Farnsworth made the world's first working television system. The basic idea of television is radio with pictures. Television is really a three-part invention: the TV camera that turns a picture and sound into a signal, the TV transmitter that sends the signal through the air, and the TV receiver that captures the signal and turns it back into picture and sound. TV creates moving pictures by repeatedly capturing still pictures and presenting these frames to your eyes so quickly that they seem to be moving. Almost all TVs in use today rely on a device known as the cathode ray tube or CRT to display their images. An antenna on your roof picks up radio waves from the transmitter. With satellite TV, the signals come from a satellite dish mounted on your wall or roof. With cable TV, the signal comes to you via an underground cable. The incoming signal feeds into the antenna socket on the back of the TV. The incoming signal is carrying the picture and sound for more than one station. A circuit inside the TV selects only the station you want to watch and splits the signal for this station into separate audio and video information, passing each to a separate circuit for further processing. The electron gun circuit uses the video part of the signal to recreate the picture filmed by the TV camera. The circuit fires 3 electrical guns down a cathode ray tube, like a fat bottle from which the air has been removed. The electron beams pass through a ring of electromagnetics. Electrons can be steered by magnets because they have a negative electrical charge. The electromagnets steer the electron beams so they sweep back and forth across the screen line by line. The electron beams pass through a grid of holes called a mask, which directs them so they hit exact places on the screen. When the beams hit the phosphors on the screen, they make red, blue or green dots. Elsewhere, the screen remains dark. The pattern of red, blue and green dots builds up a colored picture very quickly. Audio information from the incoming signal passes to a separate circuit. The audio circuit drives the loudspeaker so they recreate the sound exactly in time with the moving picture. Thermometer. A thermometer is a device used to measure temperature. It is based on the idea that metals change their behavior in a very precise way as they get hotter. While the Greeks made simple thermometers as early as the 1st century BC, it wasn't until Galileo that a real thermometer was invented. It was a full century though before thermometers had a fixed scale. This was provided by German physicist Daniel Fahrenheit, who in 1714 invented the mercury thermometer. Mercury thermometer. The simplest thermometers really are simple. They are just very thin glass tubes filled with a small amount of mercury, a rather special metal that's a liquid at ordinary everyday temperatures. When mercury gets hotter, it expands by an amount that's directly related to the temperature. So, if the temperature increases by 20 degrees, the mercury expands and moves up the scale by twice as much as if the temperature increases is only 10 degrees. All we have to do is mark a scale on the glass and we can easily figure out the temperature. How do we figure out the scale? Making a Celsius thermometer is easy because it's based on the temperatures of ice and boiling water. These are called the 2 fixed points. We know ice has a temperature close to 0 degrees while water boils at 100 degrees Celsius. If we dip our thermometer in some ice, we can observe where the mercury level comes to and mark the lowest point on our scale, which will be roughly 0 degrees Celsius. Similarly, if we dip the thermometer in boiling water, we can wait for the mercury to rise up and then make a mark equivalent to 100 degrees Celsius. All we have to do then is divide the scale between these two fixed points into 100 equal steps. Typewriter. A typewriter is a writing machine that produces characters similar to typeset print by means of a manually operated keyboard that actuates a set of raised types which strike the paper through an inked ribbon. The first really successful machine was invented by Christopher Latham Scholes of Milwaukee, Wisconsin in 1868. What happens when you press a key? Here's the typewriter with the top cover removed. The keyboard is at the front. The paper moves from left to right on the carriage at the back. In between is a complex arrangement of levers and springs. A typewriter like this is completely mechanical, powered entirely by your fingertips. It has no electrical or electronic parts. So, how do you use it? The basic idea is simple. You press a key and a lever attached to it swings another lever called a type hammer up towards the paper. The type hammer has the slug of metal type on the end of it. Each hammer has 2 characters on it. Normally, the lower character strikes the page. If you press the shift key, the carriage tips up and back so the upper character hits the paper instead. Just as the type is about to hit the page, a spool of inked cloth called a ribbon lifts up and sandwiches itself between the type and the paper, so the type makes a printed impression as it hits the page. When you release the key, springs make the type hammer fall back down to its original position. The carriage moves one space to the left, so when you hit the next key, it doesn't obliterate the mark you've just made. The carriage continues to advance as you type until you get to the right edge of the paper. Then a bell sounds and you have to press the carriage return lever. This turns the paper up and moves the carriage back to the start of the next line. Why are the keys on a typewriter or a computer board arranged in such a strange way? If you've ever typed quickly on a mechanical typewriter, you'll know the reason. The type hammers move up and down so quickly that they can collide and jam together. To reduce the risk of that happening, the designer of the first popular typewriter, Christopher Latham Scholes, rearranged the keyboard so letters often used spaced widely apart. For example, if you type the word probably very quickly, your fingers have to keep leaping from one side of the keyboard to the other as you go from one key to the next. That gives each type hammer time to fall back down and get out of the way of the next hammer that's about to rise up, reducing the risk of a jam. Now, computer keyboards are entirely electronic. There's no reason at all to keep the QWERTY keyboard layout. We keep it because most people know it, and for no other reason. It's a charming quirk of history, and long may it remain so. Cell phones. Although they do the same job, landlines and cell phones work in a completely different way. Landlines carry calls along electrical cables. What's different about a cell phone is that it can send and receive calls without wire connections of any kind. How does it do this? By using electromagnetic radio waves to send and receive the sounds that would normally travel down wires. In 1947, Bell Labs was the first to propose a cellular network. Bell Labs installed the first commercial cellular network in Chicago in the 70s. In 1973, Martin Cooper of Motorola made the first cell phone call using his 28 lb prototype Dyna TAC phone. Cell phones are a bit like two-way radios. A cell phone handset contains a radio transmitter for sending radio signals onward from the phone and a radio receiver for receiving incoming signals from other phones. Because the radio transmitter and receiver are not very high-powered, cell phones cannot send signals very far. This is one reason why cell phone masts are necessary. With their huge, high-powered antennas, they can pick up faint signals from many cell phones and route them onward to their destinations.
When you speak into a cell phone, a tiny microphone in the handset converts the up and down sounds of your voice into a corresponding up and down pattern of electrical signals. A microchip inside the phone turns these signals into strings of numbers. The numbers are packed up into a radio wave and beamed out from the phone's antenna. The radio wave races through the air at the speed of light until it reaches the nearest cell phone mast. The mast receives the signals and passes them onto an exchange building from where they are routed onward. Calls made from a cell phone to another cell phone on the same network travel to their destination by being routed to the mast nearest to the destination phone and finally to the phone itself. Calls made to a cell phone on a different network or a landline follows a lengthier path. They have to be routed into the main telephone network before they can reach their ultimate destination.